Hello everyone, and welcome to today's chem lesson. Today we are going to spend our time focusing on the idea of polarity, looking at how that applies to bonds, and also, in a bigger picture sense, how it applies to molecules. Before we dive in and talk about polarity, we want to be able to actually define it, right? So let's take a look. Polarity, when we're talking about it, it is the discussion of distribution of electrons. Are they distributed equally? Are they spread evenly throughout the bond or spread evenly throughout the molecule? Or are they bunched up and gathered in one place in the molecule or gathered in one place in the bond? And so, for example, let's take a look at two different cakes. Right here we've got this cake and also this cake. And for all intents and purposes here, these cakes are the same. We're going to put some icing on these cakes. The first cake is going to have icing that looks like this, which, to the best of my ability, is evenly spread across the top of the cake. This cake has icing that is not evenly spread over the cake. Alright. So now each of these situations is different. Each one has positives and negatives, right? Each one has bonuses, cons, pros and cons. But these two cakes are definitely not the same. This cake on the left has icing that is evenly distributed, which means if I take this slice of cake and compare it to this slice of cake or this slice of cake, I get the same ratio of cake to icing. Some people love that. Some people think that this is the fairest way to do a cake. Right? I want everyone to be able to take a slice that has the same ratio of cake to icing. That way no one gets, the end with too much icing or the part with too little icing. The distribution of icing is a non-polar cake. The icing is spread evenly. There is no more icing than any other spot. This cake on the right is definitely different. Right? This cake, if I take the first slice from the left and compare that to the last slice from the right, the first slice here has a way more icing than the first slice here has a way more icing than. When they get this icing, they're happy, right? They want a piece of cake that has so much icing on it. Other people hate icing, and so they want a piece of cake with a very little or even no icing on it. And then people have varying levels of icing adoration, right? Some people like it a little bit, some people like it more than a little bit, right? And this method of cake icing allows for everyone to get the slice of cake with the amount of icing that they want, right? Which is a benefit for this style. But no matter who is taking a slice of cake, this cake is definitely not evenly distributed in terms of icing. That makes this a polar cake. Now, when I take this comparison of cake and icing and I apply it to chemistry, I'm going to be talking about electrons and how those electrons are distributed. For non-polar covalent bonds, right, focusing on bonds first. For non-polar covalent bonds, we are talking about a bond where the electrons are shared equally. They are equally distributed throughout the bond. right? This means if we pull iodine for an example, right? If we draw the Lewis dot diagram for iodine, it looks like this. I should be focusing in on this bond. Right, so we're going to zoom in on that bond. Ignoring everything else, we just get this bond. And when I zoom in on this bond, and I know that the electrons are shared equally, I know this is a nonpolar bond because I'm telling you it is, right? This is the one we're using as our example. The electrons in this bond are exactly in the middle of the two iodines, right? Perfectly in the middle. And we know this, we can tell this is a fact because iodine has the exact same pull, the exact same strength as iodine, right? They're two copies of the same element. Because they are the same element, they will have the same pull on electrons. They will have the same electronegativity. And that electronegativity, the fact that it's the same, means that one of them is not stronger than the other, means that when they're both pulling on two electrons, right, if you have a tug of war with yourself, no one wins. You stay for all eternity at the halfway point. And so if you look, all of our examples here, right, Br2, I2, N2, Cl2, H2, O2, F2, all of these examples are molecules where it's an atom bonded to another copy of the same atom. Right? That makes the bond nonpolar. That makes us have this even distribution of electrons. Now, for a polar bond, right, we're going to put water up here. For a polar bond, we're looking at basically every other bond. Right, if I zoom in on this bond in a water molecule and ignore everything else, I get an O bonded to an H. There's still two electrons between this O and this H, right? The bond isn't different. It's still a one from each. But now we have two different atoms. O is not the same thing as H, right? Oxygen and hydrogen are two different things. Because they are two different things, they will have two different electronegativities. They will have a strength that is not the same. In this case, oxygen is stronger than hydrogen in terms of electronegativity. And so these electrons that were in the middle of the two iodines are actually much closer to the oxygen than the hydrogen. Right? In this case, the electrons here are not the same distance away from our two atoms. And that makes the bond polar, right? That's this, with our uneven icing distribution. Right? The electrons are not shared equally. And this particular example here is an exaggeration, right? It's not right up on the oxygen. There are varying degrees of polarity. You can have something that's 50-50, and then you can have every other combination. You can have 40-60, 30-70, 20-80, 10-90. We could go up by fives, right? We can have any varying degrees of polarity, any varying degrees of unequal sharing of electrons. Basically, everything that isn't a 50-50 split is polar. So let's apply this. Let's take a look at some examples. Here, I have for you ammonia, NH3. Are the bonds in this molecule polar or nonpolar? Here we're looking at two different atoms connected together, and that is going to leave us with polar bonds. Right? N and H are two different things. They have two different strengths, and so the electrons in this bond are not evenly distributed. They are not right in the middle. What about CH4, methane? Are the 4 bonds in methane polar or nonpolar? Here again, we end up with polar bonds. We have carbon connected to hydrogen. C and H are not the same thing, and so they have different strengths. One of these is pulling harder than the other. We have an uneven sharing of electrons. Right, that's true if we look at any of these 4 bonds, right? They're all C connected to H. They're all polar bonds. What about CH3Cl? Polar or nonpolar bonds? Here, for the 3rd time in a row, we still have different things connected together. None of these are connecting an H to another H or a C to another C. Right? This first bond here is a C to an H. Different things. That's a polar bond. This and this are both C to an H. Different things. Polar bond. This, a C to a Cl. Different things. Polar bond. Right? So all of these are polar bonds. Hydrogen, H2, polar or nonpolar bond? So here we have our nonpolar bond. Right here we have an H connected to another H. Exact same pull, making it a nonpolar bond. There is no pole here, right? They're exactly in the middle. Right. I know that the wording, right, having something that's non-polar be the same, where something that's polar is different, I know that that can be a little confusing. But the idea here is there a polarizing thing? Is there something where one person can have a different amount than another? Or is everything evenly spread out, and so there is no way for anyone to get a different thing? Right, we could add this, right? We could say polarizing and non-polarizing as a way to think about it, right? This cake has a slice that you want and slices that you don't want. Right? So if you're a person who loves icing, you want this slice and not this slice. Right? This is a polarizing cake. Uneven distribution. this cake over here is non-polarizing. If you walk into the party and this is the cake that they have, cool, right? No matter who you are, no matter what you like, you get a slice of this cake. Right? You're not going to fight for one slice over another. They're all functionally the same. Right? It is a non-polarizing cake because the icing is evenly distributed. Right? We're not going to... Right? This is not short for polarizing and non-polarizing, but it is a good way to talk about the differences between those two terms. Right, this bond, because we have the same thing on either side, means that these electrons are smack in the middle, making it a non-polar bond, even distribution. What about HCl? Is this bond polar or non-polar? Right here we have a polar bond. Two different things pulling on the electrons. Chlorine is much stronger, so those electrons are going to be much closer to the chlorine, not in the middle of the bond. Right, these electrons end up bunched up on one side. And so when we talk about polarity, we started focusing on the bond, but we can also take a step back. We can zoom out and look at the molecule as a whole and talk about, right, so these electrons are polar, right? That's a polar bond, so the electrons are bunched up closer to the chlorine. But are the electrons in the whole molecule spread evenly? And that's the question that we are going to answer next. Right, when we talk about polarity, we can zoom out. We can look at the bigger picture. We can look at the molecule. And so, we're going to do that. We're going to look at CO2, which looks like this. And we're going to look at water, which looks like this. And we're going to try to talk about symmetry in a molecule. Right? It's still the same idea. We're still talking about that cake and the icing. Is it evenly distributed or not evenly distributed? But we're looking at the whole molecule now as opposed to focusing on just the bonds. And before we jump into what it means to be a symmetrical molecule or an asymmetrical molecule, I want to remind us what we're talking about. If I pull up the chemical symbol for bromine, this lettering represents an atom, which is a nucleus, which I'm going to draw much bigger than I should. Right? It represents this sphere, this nucleus, and all of the electrons that surround it. Right? So there's the electrons in the rings that we are going to put out there. Right, but let's focus on the nucleus of this atom. Right, this lettering, this B and R, represent an atom. And so when I want to draw and see if there is symmetry, if I put this line of symmetry, right, artistically, these are not symmetrical. Right, you can't put a line of symmetry here between the B and the R. But if we think about what this lettering represents, and I put a line of symmetry vertically through a sphere, this is symmetrical. The letters that we use are representative of something else. They are representative of these spheres. So a line of symmetry that cuts an atom's lettering into halves is still symmetrical, even if it's not artistically symmetrical. Same thing here. If I put a horizontal line of symmetry here, this R doesn't get reflected. This is not an artistic line of symmetry. But if I think about what this represents in terms of a sphere, it is a line of symmetry, right? Half a sphere is equal to half a sphere, right? This does mirror over onto itself. And so we're going to talk a lot about lines of symmetry in the next couple of minutes. And I just want to remember, these are both lines of symmetry for bromine, even though they don't artistically represent lines of symmetry, because they are representative of spheres here. But we can't just do all of our drawings as sphere connected to sphere connected to sphere, because then how are we going to know what atom is which? And so, when we talk about the polarity of a molecule, when we zoom out and stop focusing on the bond and instead look at the molecule, we can tell if the electrons are evenly distributed if there are multiple lines of symmetry in the molecule. Right? A symmetrical molecule is nonpolar if it has two or more lines of symmetry. And so if I look at CO2, there is an artistic line of symmetry I can draw, right? Pretend I can draw straight lines here, right through the middle of the carbon dioxide. That is an artistic line of symmetry. Right? This perfectly folds over onto itself. I can also put a vertical line of symmetry in. Even though the carbon isn't, right, symmetrical, even though that C doesn't fold onto itself in the vertical plane like this, the sphere that it represents does fold over onto itself like that. And so this is a second line of symmetry for carbon dioxide. Right, I get these two. Oh, that was worse. That was way worse than the first one. I get these two lines of symmetry in carbon dioxide. And once I see that there's two, I know that it is a nonpolar molecule. On the other hand, an asymmetrical molecule is polar. It means that there is an uneven distribution of electrons. And if there is only 1 or 0 lines of symmetry, we know that it is polar. So for water, I can put this artistic line of symmetry through the top, but that is the only line of symmetry I can draw. And because it only has symmetry in one direction, it is a polar molecule. It tells us it's a shortcut for us to know that the icing on this cake is not evenly spread out. Let's look at those same molecules we looked at before, and this time figure out if the molecule is polar or nonpolar. Right, here is NH3. We already know that the bonds are polar. Is the molecule as a whole polar or nonpolar? this molecule is a polar molecule. I can only put one line of symmetry in this molecule. Right, to be nonpolar, it would need 2 or more. Right, this vertical line of symmetry is the only one that I can make. Right, again, it doesn't matter that the N is not a perfect fold. Right, this is a sphere that we're talking about. And so this line will divide that sphere in half. Right, what about CH4? Is this polar or nonpolar? This is a nonpolar molecule. We can put multiple lines of symmetry in this thing. We can put one vertical. We can put one horizontal. We can stop there. Right? Once we have 2, that's the boundary that tells us, well, we're nonpolar. But there are also diagonal lines of symmetry in this molecule, actually. Right. Horizontal and vertical, we actually get the same set of symmetry. Right? Half of a hydrogen on either side, half of a carbon connected to a full hydrogen on one side. At the diagonals, we get another set of symmetry, where this time it's half a carbon, but also 90-degree angle connected to 2 hydrogens. Right, so even though these bonds are polar, right, we figured out that those are polar bonds, the molecule as a whole is nonpolar. Right, that's okay, that happens. What about CH3Cl? This is a polar molecule. Right, when I go to cut through, I can only put a line of symmetry horizontally. Again, please forgive my terrible garbage lines. But I can only put one line of symmetry. I can put it horizontally. There's no other lines of symmetry I can make, which makes it a polar molecule. Hydrogen, H2. This is a nonpolar molecule. I can go horizontally. Jeez, I can do better than this. I know I can make straighter lines than that. There you go. All right, a horizontal line of symmetry, and also a vertical line of symmetry. 2 lines of symmetry tells me nonpolar. Last but not least, HCl. Is this going to be a polar or nonpolar molecule? Here, our final example of a molecule is a polar molecule. The only line of symmetry that we can draw is horizontal. There's no other way we can slice this up that makes it symmetrical. All right, if we try for the vertical line of symmetry here, yes, we get an atom on the left and an atom on the right, but these are very differently sized and shaped atoms, and so that doesn't work. All right, even though we can cut a sphere in half, at any angle here, this is the only symmetry that works. If we go for a vertical one, we're putting a very small sphere on top of a very big sphere, and that doesn't work. In our upcoming lessons, we're going to talk about how this plays into the properties of these compounds. Right? What does it mean if a molecule is polar? How does that affect the way it interacts with itself, with other things? Right? We're going to bring that up in our discussion on intermolecular forces next time. But for now, I'm going to ask everyone to transition over to our Google Meet for questions, comments, concerns, and attendance. And I will see you there.